All right, we're out of kind of the basics of trigonometry, but now moving forward, we want to look at other places we can kind of incorporate trigonometry into math. And one of the first things that comes up is the polar coordinate system. Before we explain what it is and how we're going to use it, I want to look at just kind of why, like what's kind of cool about it. It's a completely different system of graphing points. We're used to the rectangular system, where you got your x and your y, and x means you go horizontally in that distance, and y means you go vertically that distance. You plot your point. Polar is going to be a little bit different, and what's cool is we start to get graphs like this with some very simple equations. We get these cool looking graphs. So here's some examples of some polar graphs that you can make very easily with a graphing utility. And we're going to make some of these by hand probably, but here are some examples. You can make things like this, and they can just keep getting more and more complex. You can make these flowers down here, and the associated equations are there. So again, currently we have these two systems, okay, of graphing points. And this one is our rectangular system. And the way that rectangular system works is we have two axes, and we call this axis the y-axis, or the coordinate, and then we call this the x-axis. This is our coordinate system. So, we write points like this as ordered pairs. That means I go over 2 and up 3, and there's the point 2, 3, and so on and so forth. Our new system is going to be called a polar coordinate system. And the way we're going to graph points here is like, say, for a location, this is graphing paper on polar coordinates, right? We're going to talk about the center right here. That point is called the pole. You can imagine like we're looking down on a pole, like on top. I always kind of think of like tetherball. If we were looking down on a game of tetherball and it's got a string attached to the ball and it's somewhere out here, that would be our location. And instead of using like, how much right and how much up we go, or how much left and how much down we go, we're going to just talk about how far is our location back to the pole. All right, so a lot of times this will be important, is like just how far are we from, say, home or whatever, from the pole. So that's called the pole. Okay, and then we're going to talk about like this point out here is this location. We can call that point A. We've got a point over here. That's a location. And we're really going to just keep referencing how far are they back to the pole, or how far are they from the pole. That's why it's called polar coordinates. This to me sort of looks like if you were looking down on the North Pole, those are like your longitudinal lines that spread out. All right, so this is called the pole. And then we're going to have something called the polar axis, and we're going to have it run out this way, and that's at an angle of 0 radians. And that polar axis never moves. That's like our initial ray when we rotated angles around in our coordinate system before, in our unit circle. And so now what we're going to talk about is we've got our polar axis. Whoops, let me write that a little more neatly. So we've got our polar axis there. And we're going to talk about how we write these points. So the coordinates are going to be written as r theta. And we are going to look at basically how do we plot this point. And what it's going to mean is, first we're going to figure out how much we rotated from the polar axis, and then we think of that ray. So that'll be what our theta is. Okay, so our theta is an angle from the polar axis. And then we're going to talk about r. R is the directed distance from the pole. So this is called polar coordinate, like graph paper. It helps you a little bit. So we kind of think of this as being 1 unit when you get out to this part here. And then when we keep going along this, on this angle, we keep going along this ray. That would be 2 units out. And then that would be 3 units out. Okay? So this is our theta, and this distance here is our r. So we've got kind of a radius and a theta here. How much did we rotate, and then how far away from the center pole are we? All right, so here you want to pause the video and write down the method for plotting polar coordinates, and then we're going to do some practice. All right, so welcome back. Let's do some practice. So step 1 says to start on the polar axis. So again, our polar axis is right here. And we're going to first look at our theta. We're going to rotate to pi over 4. And then we're going to move from the pole 3 units out. Now, we said directed distance before, right, up here. The directed part will come into play. We can also go in the negative direction, but for right now, 3 is positive, so we're going in the positive direction. So if I start here and I move along this angle, pi over 4, that's 1 unit. That's 2 units, right? That's 1, that's 2. There's our 3rd unit. So that's the point 3 comma pi over 4. We rotated pi over 4 units from the polar axis. Then we moved along that ray 3 units away from the polar axis. And that would be our point there. That would be the coordinates in polar, right? So maybe just to show you, I kind of wrote in how we got there, but I don't need all that. I could just say like that's the point, and the way I get there is by how much I rotated, right? And then how far I am from the pole or the center. Here's an example, a different example. So I've got 2 points already on the grid. Could you write the coordinates of the ordered pair using polar? So again, here is, using polar coordinates. We're going to look at first how much we rotated to get out here on this ray. And this polar graph paper is nice. It's already got the angles marked off for you. So point A has the polar coordinates 3 pi over 4 is our angle. And then how many units along this ray did we move? We went 1, 2 units. So that's the coordinates of A. What are the coordinates of B? B, I got to rotate all the way around and come to here. And it's on that ray. And that's going to be an angle of 5 pi over 3. It's nice that they already gave me that there on my polar coordinate paper. And then how many units from the pole? I go out 1, I go out 2, I go out 3 units. So those are the coordinates of points A and B. All right, so this one you're able to plot given the coordinates. Here you're given a plotted point. Can you write the coordinates? All right, so now the nice thing about polar coordinates, one thing is that we can represent the location of a point in more than one way. I can use more than one ordered pair. So that is not true of rectangular. Keep in mind, like if I use the old rectangular system, let's go back to our point 2, 3. That's the only way I can represent that location. 2, 3. I can't, if I say like negative 2, 3, I now have a different point. I'm over here. It's not the same location. That's not true of polar. So let's look at the 2 different ways that you can get to the same point. What happens when r is negative? R can be a negative number. So let's plot this point. So our polar axis is right here. Our pole is in the center. I rotate to 5 pi over 4, which is right here. And there's that ray. But now, how do I go negative 3 units? So I'm not going to move 1, 2, 3. That's the positive direction. The negative direction is if you move in the opposite ray. So I'm going to go this way for negatives. I've rotated to 5 pi over 4, but now I'm going to kind of go backwards or out in the opposite direction. 3 units. 1, 2, 3, and I end up here. And notice that this location, -3, 5 pi over 4, is the same location as our example 1, 3 pi over 4. So a point in the same location can have two different sets of polar coordinates, depending on if, like, I can make my radius negative. I can rotate. It's always going to be pi more, pi radians past where the angle I want, and then just go backwards by using a negative radius. Or you can say you're going to go a half a rotation around, but then go negative. So that's one way to get to the same point. All right? Plot this one. So how about this? I can get the same point. Instead of making my r negative this time, I can just add rotation. So if it's 9 pi over 4, I've got 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4 is right there, 8 pi over 4, and then 9 pi over 4. I'm back here. So I just added one full rotation. Oh, sorry, this is from my polar axis. Then I go out along this ray because 3 is positive, so I go out in that direction. 3 units, 1, 2, 3, and there I am. And the coordinates of that point are 3, 9 pi over 4. So here's yet another way to write the same point. I can go 1/2 rotation further and make the r negative. I can keep the r the same but go 1 full rotation. And then, of course, here was the first most simple version. And there's an infinite number of ways I can write these points. I could have started at the pole and went negative, right? And then graphed it that way. So I want you to pause the video here and see if you can write this location in two more ways for a little bit of a challenge. For this same location, 3, pi over 4. I just gave you some ideas with the negative, but can you come up with some other ways? Come up with 2 more. There's infinite amount of ways. I'd love to hear them in class, what you came up with. All right? So in general, the kind of easiest way to do this is if I ask you to find like more than one representation, is going to be one way. If I give you coordinates and say find 2 others for that same point, you can first add 2 pi, or if it's in degrees, 360 degrees to the angle and not change r. So for instance, r theta would be equal to not changing r but then adding 2 pi onto theta, okay, or 360. All right, so this is equivalent to adding 1 full revolution, right? That's one way. A second way to do it is to add a half a rotation, so add pi to the angle. And I should say add pi or 180 if it's in degrees. And replace r with negative r. So that would look like this. My original point, r theta, would equal negative r, right? I would change that to a negative, and then it would be theta plus pi. This accounts to adding half of a rotation. And that negative r is that directed distance. You're going to go in the opposite direction. So let's look at this in practice. So first, let's plot the point 2, pi over 3. So I like to figure out the rotation first. So pi over 3, we start here at our polar axis. Pi over 3 rotates to there. So now we're thinking like we're along this ray there. And now I'm going to go 2 units out. So I go 1, 2, there it is. That is my point. It's 2 pi over 3. Okay. Now for part A, they want us to find an r that's positive and the theta that's between 2 pi and 4 pi. So what I'm going to do is I'm going to add 1 full rotation to this, end up at the same spot. So, and not change r at all. So my r will still be 2, but if I add one full rotation onto pi over 3, it's going to be pi over 3 plus 2 pi. So I can rewrite that as 2. And then pi over 3 plus 2 pi, I'm thinking of pi over 3, I'll just do it here. Pi over 3 plus, if I change this to over 3, it's going to be 6 pi over 3. So then it's going to be 2, comma, 7 pi over 3. Okay, so that fits my criteria. R is positive, and now I have a theta that's in between 2 pi and 4 pi, because 7 pi over 3 is in between those two. Now they want us to do one where r is negative, right? And we'll deal with the angle in a second. But if r is negative, that means when I do my rotation, I got to stop here, get my ray going in this direction. Sorry. I want to stop here on the opposite side, because now if I'm going to go in the opposite direction, if r has got to be negative, instead of sliding down the ray this way, I've got to go down the opposite ray, -2 units. So -1, -2, right? So that's how I'm going to do that. So it's going to be -2. And then what angle do I stop at? This is going to be, since I want it to be opposite of pi over 3, I'm going to basically add a pi onto that. That's how I can think of that, right? Because it's a half a rotation past the original angle. So pi over 3 plus pi. I could just figure it out by looking on the graph paper, but I like to try to apply this idea here, that if I add a half rotation and make my r negative, I'll get to the same spot. So it's going to be -2, and then pi over 3 plus, if I turn this into pi over 3s, it's going to be 3 pi over 3. So it's going to be -2, 4 pi over 3. And that fits my criteria. R is negative, and theta is in between 0 and 2 pi. So that's another way that I can get to that same location. Let's look at the last one. R is positive, but this time theta's got to be between -2 pi and 0. So I want to make my rotation negative. So now what does that mean? To get to this location, I'm going to start by rotating in the negative direction, and I'm going to stop here. And I'll be on this ray, and then R will be positive, so I can go in that direction. So it's going to be 2 because R is positive. And what's that angle? That angle is going to be negative, and I rotated, if it's pi over 3, it's really going to be what? -5 pi over 3? Because it's one short of being -6 pi over 3. So that's another way to list the same location. So the big idea here is that rectangular coordinates, there's only one way to label that point. Okay? For polars, there's all different ways to label the same point. And here's a couple examples of that. So you do your best to follow through with all these examples. If you have questions, that's why we're going to be doing this again in class. This is my introduction to the topic. So keep in mind this idea of watching and taking notes on the video. You're not supposed to know everything I'm talking about, but you're supposed to be able to follow along, take notes. And so the questions we ask in class are like deeper questions. They're more about like the specifics of how did you get this part or why does that work. It's not going to just be, wait, what's R mean? Okay, and if that is the case too, that's fine if you're asking that. So don't get stressed out if you're not following every single thing I say. Do your best, and you can always ask questions in class. We're going to try to straighten out any issues you have with what's happening here. All right, so moving along, we want to look at the relationship now between polar and rectangular coordinates. So if I line up my x and y coordinate system, and I put the polar coordinate system right on top of it, where I make the pole line up with the origin, and I put my polar axis right on the x-axis, we can kind of use two different ways to represent the same point. So I'm going to pick a random point out here, and I'm going to give its coordinate locations because we're used to that, x, y. And we know that that means, actually, I'm going to do the coordinate locations of rectangular in this pink color, x, y, and we know that that means we go over x units and then up y units, and it makes a right angle. And that's one way to get to that location. We go right x and up y. A second way to get to that location, and I'll do these in blue, is to use polar coordinates. I could start at the polar axis, and I can rotate theta degrees, I'm sorry, not degrees, theta radians, and that kind of makes our polar ray. Actually, I don't want it to go past. I want to kind of just stop there. And then we say we move our units along that ray till we get to the point. So those another way to list the coordinates are going to be r comma theta. Two different ways to represent the same location. Okay? And one of the goals is going to be, can you convert back and forth? If I give you rectangular coordinates, can you write me the polar coordinates and vice versa? And it's going to come down to some relationships here. So some things we notice from this picture. Looking at, oh, sorry, I thought I just lost power. Okay, looking at the right triangle, we have our Pythagorean theorem, of course, right? X squared plus y squared equals r squared. We're definitely going to use that for something. Okay? Other relationships that we notice, we could say things like sine of theta using some trigonometry equals opposite over hypotenuse, so y over r. Cosine of theta equals adjacent over hypotenuse, which is x over r. And tangent of theta is equal to opposite, which is y, over adjacent, which is x. Okay, these kind of four things will help us do our conversion. And you can see why now this comes right after trigonometry. There's a lot of trigonometry involved here, especially with the whole converting back and forth. So I'm going to look specifically at, let's see, which way do we want to go first? Do we want to go from rectangular to polar or polar to rectangular? I think I want to convert from rectangular to polar, I think, first. No, let's do it the other way. Let's do polar to rectangular. Sorry. I think that's the one that's where we should start. Polar to rectangular. So we're going to specifically look at these two equations. Sine of theta equals y over r. I could solve that for y by multiplying both sides by r, and I get r times sine of theta. Similarly, I can say cosine of theta, oops, I should have parentheses there, equals x over r. So I can solve for x and say x equals r times cosine of theta. This is important because these are sort of like functions where your input is the r and theta. And what do you get out for an answer? You get a y coordinate as your answer. So just putting the two on top of each other on the same grid, and then playing around with our sine and cosine ratios, I end up with a really nice clean formula that will take the r and the theta, if I know them. I can plug it in and it'll spit out my y coordinate. I can do the same thing. I can take that same r and that same theta and input them into this equation, and it's going to spit out my x coordinate. And then once you have your x and your y coordinate, you've just converted. So let's look at an example. I want to keep my numbers consistent. We're on example 6. Example 6. Find the rectangular coordinates of the points with the following polar coordinates. Let's start with A. We've got 2 comma, that's in 3 pi over 2. So 2, that's our radius, and that is our theta. We're in polar. So now to convert, we want to say that to find our x coordinate, it's going to be r cosine of theta. And that's easy to remember because we kind of relate our x with our cosine, right? So that's going to work out nicely. We're going to multiply, the r times our cosine value of theta. So We've got x equals 2 times the cosine of 3 pi over 2. So that's going to be equal to, let's see, cosine of 3 pi over 2 is 0. So then 2 times 0 equals 0. So our x-coordinate, I'll keep track of our answer right here in the middle. Our x-coordinate is now 0. Now for our y-coordinate, we're going to say y equals, let me buy some more room here. Y equals r sine theta. And again, it's easy to remember because we've already associated kind of r with our sine values, right? So y is going to be, I take my r from my given polar coordinate is 2 times sine of 3 pi over 2. So what does that equal? 2 times sine of 3 pi over 2 is what? -1. So then 2 times -1 is -2. So now we have our y-coordinate is -2. So there we go. This is our answer. These two locations are the same exact location. One's using rectangular and one's using polar. So let's take a look at that. If I graph it, I'll graph first the rectangular. 0, -2 is right here. If I do polar, it says rotate from the polar axis, which will be right here. Rotate 3 pi over 2, which gets me here. And then move 2 units in that direction, 1, 2. And we arrive at the same location. Okay, so they're the same point. All right, let's look at another one, example B. I'm going to say pause the video here and see if you can convert this one on your own. This one's a little trickier. I put a negative in there, but you still just follow your formulas. Your x equals r cosine of theta and your y equals r sine theta. Take a second, pause the video, see if you can get these. All right, welcome back. So you should have gotten -4, -4 root 3. Again, if you're having trouble with this would be a spot where you'd ask for your teacher for help the next day in class. Like, hey, how did you get that? I'm not going to go over that one. We're going to do converting in the other direction as this video's approaching 30 minutes. All right, so that's how you go from rectangular, from polar to rectangular. And these are your two formulas. Those are important. Okay? Now let's go the other way. From rectangular to polar. If we come back up here to our picture when we drew stuff on top of each other, we didn't really get to use these two equations, right? So we're going to snag those. We're going to snag that Pythagorean theorem. And we're going to snag that tangent of theta equals y over x. So these are good because I can solve for r on this Pythagorean theorem pretty easily by square rooting both sides. And so you see that what you input here is your given x and y from rectangular. You plug those in, and what it spits out is your radius. So for polar, it gives you your r. All right, so this is the equation used to find r. This equation, you input your x and your y, and then you solve for theta, and then you get your theta, which gives you your rotation. You put those two answers together, and you get r comma theta. Now, some people will say that the way you find your theta, you might see theta is equal to inverse tangent of y over x, and we'll talk about that in class a little more in depth. There's a little bit going on there. We're going to just focus on solving that equation for theta right now. All right, so let's do an example. What example are we on at this point? Example 7. All right, so find polar coordinates. I shouldn't say the, because there's many different forms. I'll just say find polar coordinates for the point whose rectangular coordinates are -1 root 3. My first suggestion here is you got to know when you're talking about theta, right? We want to end up with an r and we want to end up with a theta. And when you're talking about theta, it's important to know what quadrant you're in. And we're kind of given that right off the bat here, because when we say -1 root 3, that means like we can go over 1, so -1, and then up root 3 is a little bit bigger than 1, right? So I don't know, it's like right there. So that's -1 root 3. And I even kind of like to have that triangle going. It's -1, it's root 3, and that's my r, right? So I like to draw that triangle. They gave us these rectangular coordinates. So if you just think of it like this, you're really just doing Pythagorean theorem. Like you can memorize your little formula right here, but it's really just Pythagorean theorem, right? If you draw the picture, it's easy to find r. You do Pythagorean theorem on this guy, and you now have your r. So let's start with that. We plot the point as step 1. Step 2, we're going to then do our Pythagorean theorem on this to find r. So to find r, we're going to go root 3 squared plus -1 squared equals r squared. Again, you could just plug it straight into this formula if you want as well. It's all the same thing. Root 3 squared is 3. 1 squared is 1, so I get r squared. 3 plus 1 is 4. So I get r equals 2. And we always want kind of that positive distance. I mean, we can make it negative depending on where we end up with our angle. So for right now, we're just staying with 2. So as I write my polar coordinates here in polar form, my r is 2. So this is going to be my answer. Now I just got to come up with my angle. All right, so now to find theta, we're going to use this relationship. Tangent of theta is equal to opposite over adjacent, essentially. So again, with the picture, it's pretty easy to figure out. So to find theta, I go tangent of theta is going to be equal to opposite over adjacent. All right, so that means tan of theta is going to be equal to -root 3. And then we have to solve that equation and then account for the proper quadrant. So we know there's a couple ways to come up with what angle this is, but we know that theta is going to be the reference angle pi over 3. Okay? And so we now have to figure out, like, again, what quadrant we're in. So we already know that we're in quadrant 2. So what's our reference angle of pi over 3 in quadrant 2? That angle is going to be, so I should just say our reference of theta is pi over 3. Our actual theta is 2 pi over 3 because we're in quadrant 2. So we've got 2 pi over 3.